Hello, my name is Tim Anderson, and welcome to my talk on exposing legacy mainframe data with GridGain and Apache Ignite. A little bit about myself before we get started. I've been a software engineer for over 10 years. The majority of my career has been spent working on mainframe systems, primarily on back-end deposits applications. My focus now is on exposing those same back-end applications to distributed and cloud systems. We are headquartered in Buffalo, New York. Part of that headquarters is the M&T Tech Hub, which is home to 1,500 tech employees, as well as the M&T Tech Academy, which is a partnership between local schools and companies to grow the next generation of developers in-house. We are one of the 20 largest commercial banks in the US. And as you can see on the map to the right, our footprint spans very far along the East Coast. Our current core banking applications have been extremely successful in processing high volume transactional and batch workloads, but they are lacking in an effective and scalable way to expose that data to distributed and cloud-based applications in a meaningful way. Thus, the cloud integration is very limited, making it difficult to expose valuable data to our customers and business partners. Previously, our methods for exposing this data relied heavily upon extracting and loading data off platform, which resulted in data often being stale or out of sync between the source system and the consuming applications. This, coupled with limited ability to expose data via APIs, made creating valuable distributed and cloud-based applications difficult. Another problem we faced was the complex data needs of the consuming applications. They would often need data from multiple legacy systems, which meant deploying any new application required a lot of effort to put together. Our upstream applications consuming this data were frequently tightly coupled with the source system data, meaning that in order to work with the data, they would first need to contact the source system to understand the data layout and the meaning of that data. Additionally, changes to that source system data would also directly affect the consuming applications. So a small change to a field size could cascade to other applications within the bank. From my experience, most approaches to solving the solution boil down to two things: replacing the source system with a modern solution, or augmenting the existing application to work well in a modern tech stack. Both solutions have their challenges, but I think replacing an existing application with a new solution without losing functionality, continuously adding new features, and not introducing any new bugs or problems can be difficult, if not impossible, to achieve. And that is why we took the approach that we did. But before we get into the solution, I want to talk a little bit about the mainframe itself and why we chose to run Ignite on z/OS and some of the key features we can take advantage of. I'm sure a lot of you here today may be unfamiliar with the mainframe and may think of it as an outdated piece of hardware. So let's put that myth to bed a little bit here. We have a Z15 mainframe at M&T Bank, which is the latest release up until this year. I've listed some of the important specs and features of the Z15 here on the left. As you can see, it has a very respectable processor speed, up to 34 processors and 40 terabytes of memory per machine, which can be scaled by sysplexing together to expand its processing power. The next two segments on this slide, I will break down in slides to come, but some of the features like fast local sockets, the zip specialty processor, and the logstream facilities provide us with some unique performance boosts to staying on z/OS, as well as the added benefits to running on the same machine as our data We eliminate much of the network latency that might exist in other solutions. So the first two ZOS components that will be good to understand are vSAM and the CICS transaction processor. The majority of our application data is stored on vSAM files, and you could think of these files as simple key value stores. It is a very basic but very fast and efficient approach to accessing data. The CICS transaction processor, sometimes referred to as CICS, can be thought of as a web and application server. It is a middleware product that we use to handle application runtime on ZOS. Requests come in to the WORs, or web owning regions, and are routed to the appropriate AOR, or application owning region, to be processed. We also have the logstream facilities available to us on ZOS, which is available to any IBM mainframe. It is a immutable system log that applications can take advantage of and write data to. We have the Unix System Services component, which is a full-blown Unix operating system on the mainframe, where we have Ignite installed and it is executed from. The ZIP specialty processors and fast local sockets are where we start to see some of the unique performance benefits we can get from ZOS. For those of you unaware, the ZOS platform, you are billed for cycles run on the general processor. ZIP processors exist outside that billing model and allow us to run Ignite on ZOS without impacting the cycles run on the general CPU, saving money, but also separating the Ignite workload from the existing application processor pool in the central processor complex. This allows for them to run on the same machine without impacting each other very much. Fast local sockets are a huge performance boost for both Ignite clients and reading data from the source system using DVM. We'll talk about DVM in upcoming slides. Fast local sockets allow for the TCP/IP traffic to bypass both the inbound processing and the IP layer of the TCP/IP stack. So the sending application places the messages directly in the receive queue for the receiving application. So now that we've talked about some of the tools and features that we have available to us on ZOS, let's take a look at the original approach that we had to solving this problem, and then we'll get into how we have augmented that solution to use Ignite and GridGain. So previously, the vast majority of our distributed applications using data on ZOS platform relied almost entirely on source system applications to create file extracts out of batch, FTP those extracts to servers where the upstream application could pick up that file, transform, and load the data. This was a very inefficient process for us. And we had no real way to stream data or emit events off platforms, making it difficult for applications to know when data had changed. The raw data was also not intelligible. And what that meant for some of our applications who wanted to consume data from us, or for business analysts or testers who wanted to verify data integrity, they would need to rely on one of the application programmers to write a report or set up a meeting so that they could go over the data and make sense of what it meant. Also a very inefficient solution. Next, let's take a look at how we designed our approach to effectively exposing the data. We chose an architecture based on the command and query responsibility segregation pattern, or CQRS. Very simply put, our read operations and write operations are separate from each other. We feel this approach provides a stable and scalable way for us to build a performant and high volume enterprise application. So now we can expand upon this model and take a look at the details of the approach. So this is the flow of data through the Digital Integration Hub. On the left, we have update operations from both on and off ZOS platform, making changes to the source system data, both in batch and real time. When that data is written to the source system vsam files, we use data propagation exits to push those changes out to application-specific log streams, which again are immutable logging facilities available to any IBM mainframe. Both the logging facilities and the source system vsam files can be mapped to virtual tables in the Data Virtual Manager, or DVM. And DVM is a product running on ZOS that is able to read from ZOS native files and map those files to a SQL-compliant virtual table that can be exposed through a JDBC or ODBC connection. We can then leverage Ignite clients to query DVM via those fast local sockets, which gives us an extremely fast method to loading that data into Ignite, where we can expose it to our distributed and cloud applications, as well as business analysts and testers in an efficient and meaningful way. So loading that data is a twofold process, where first we bulk load the entire data set out of batch to pick up all the changes from the source system. Then intraday real-time transactions are picked up via a polling service. These polling services are continuously pulling multiple times a second from multiple application log streams, looking for new records that have been written. Both of these processes are Ignite clients that then load the data into Ignite for upstream consumption, where we are able to expose the entirety of our source system application via standard connections in an easy to use way. This has provided a huge value to our distributed partners within the bank. One of the most important aspects of this approach that I think we can see here is we are only querying the actual source system files once per day in that bulk load process. The rest of the queries are against the log stream, and all consuming applications are querying against Ignite. This separation of responsibility really allows for us to push extremely high volume reads and writes at the system without overloading any one single file system. Now we can break down the components of the Digital Integration Hub. Firstly, we have the Data Virtual Manager, which is a tool we leverage to map our source system data to virtual tables, allowing for easy access to our mainframe data sets. Some of the key features in DVM that we can take advantage of are that it is zip eligible, allowing us to, again, separate that workflow and workload from our applications running on the general processor. The virtual tables are ANSI 92 SQL compliant, allowing for a standard way to process the source system data. DVM supports highly parallel access to the source system data, which provides us a very fast way to retrieve that data. The source system applications are responsible for exposing their data to DVM. And what this allows us to do is have those closest to the data to be in charge of mapping it to DVM, which we think makes the most sense from an enterprise perspective. DVM is a good first step to exposing your source system data to distributed applications, but the queries still hit the source system data directly, adding additional I/O to the system of record. This is where Ignite and its in-memory compute platform can be leveraged to extract that data. And the first step in that process is our bulk loads. The majority of our legacy systems rely on some form of batch processing. So in order to effectively pull those changes into Ignite, we have built bulk load client processing, which can load the data from the backend system in its entirety into Ignite caches. To do this, we leverage the Ignite compute interface to deploy our bulk load processes to the Ignite cluster. Both the Ignite clients and DVM connections are multi-threaded, which allows us to achieve very fast load times from very large data sets. So here we have an example of one of our bulk load processes. On the left, we have a method that kicks off our bulk load process for the RST task. The load cache job implements a Ignite callable interface that is then broadcast to the Ignite cluster. At this point, we are able to ingest the data from DVM and put it into Ignite caches. The screenshot on the right is the execution of this bulk load process. We trigger this process via a Spring command line runner, and then fine-tune some of the performance settings at runtime. This particular example, we have MRCC, which is a DVM setting for map reduce client count. And what that means is we're able to split the work of a single JDBC connection into 4 concurrent queries that each process 25% of the data set. Next, we have the GGTN, or GridGain thread number of 8, which allows us to split those 4 JDBC connections to DVM into 8 separate threads, giving us a total of 32 threads that are processing 2,000 rows at a time, putting those into Ignite. The RST load task here is actually executing 3 separate bulk load processes. And in total, those 3 bulk load processes are loading over 500,000 rows in just over 8 seconds. We currently have 22 of these bulk load processes running once a day, some loading as many as 26 million rows in just a few minutes. Then we have our intraday transactions that are pulled in from the application log stream. Our polling services are continuously looking for new records to be written out by the application. Once it detects a new record on the log stream, it immediately writes those changes to the appropriate cache. Our polling services are built using the Ignite service interface. Using the Ignite service interface and are deployed to the cluster at runtime. Once deployed, they become a continuous service running on the cluster. And now we can look at an example of one of those running services. They're started in the same manner as our bulk loads through the command line runner, where again, we're able to specify optimizations at runtime. For polling, there's a little bit less in the optimization that we need. We just have a query delay, which is the amount of time we would like to wait between checking for updates to the log stream. For this particular service, it is set to 5 seconds. We also have a service wait time, which is an additional time to wait in between querying the log stream. And that gets used if after 500 queries or some specific value that we set, we have no results back from the log stream, meaning there is very little updates happening. We reduce the time to reduce the cycles that we are using. So now that we have seen how we load data into Ignite, let's take a look at how we are exposed that data in Ignite to the distributed and cloud applications. So now our BAs and testers have the ability to verify data integrity with an easy to use and easy to understand SQL queries. Our REST API building is now much easier, and applications exposing or consuming the data do not need to know or be concerned about the layout of the data on the source system of record. Our distributed and cloud-based applications now have the ability to join together data from multiple systems of record in a single location using a wide range of standard interfaces that are supported across many programming languages and tools. And our data is available real time with minimal impact to the source system. So now if we take a look back at the original challenges that we faced, I think we have been able to solve all 4 of our problem statements here. We no longer have any limitations on our cloud integration. They are very easily stood up, and it's very easy for them to connect to and read from the legacy system now. Information delays are completely gone as our data is continuously updated real time. The data is no longer tightly coupled. The consuming applications no longer concern themselves with the data structure of the system of record, and the data is also intelligible and easy to understand what we're pulling from. The complex needs of those consuming applications still exist, but the manner in which we can put those complex data requirements together is greatly simplified by the fact that everything is stored in one location and is joinable through standard queries or REST APIs. So that concludes my talk here today. Thank you for joining, everyone. If you have any questions that I don't get to in this question and answer segment, we can continue our communications through email or on LinkedIn. Thank you all for joining.
And thank you, Tim. Let me bring you back onto the stage. So we do have a couple of questions for you to keep you on your toes.
Sure.
There's one which you kind of covered a little bit in the talk because it came through a little bit earlier, but I think it's a little bit of a simplification. So Sean Ashley asks, how much data do you store in Ignite and how many caches?
Right, so we talked a little bit about the caches we have. We have 22 of them right now total. We have over 1,000 fields in those 22 caches and about 600 gigabytes of total storage and memory. Oh, can you guys hear me?
Yes.
Cool.
Yeah, great. Right. Okay, thank you. And then Justine Jacoby asks, how do you handle monitoring the different services and the Ignite server?
Sure, we have a couple different options to us. There's some built-in logging facilities on ZOS, but we leverage the Elk stack and write all of our logging messages out to there that are monitored by a central command center that can alert us to any problems through watchers, such as maybe out of memory or a failure to a bulk load client that's running. So we get alerted real time to fix the problem and are right back online.
Okay, good. And then a question from Pascal Ioannidis. What about transactions to isolate CRUD operations with such a high volume of data?
So right now we're not using any transactional updates. All of any updates we have are through the ZOS platform with those bulk loads and polling services, and then all the read-write operations are through those REST APIs we talked about. So everything is separate. The updates come to the source system, and then just the read operations come in through Ignite.
Great. Okay. So here's another question. Are you responsible for building the APIs into Ignite?
We have some of our own that we've built ourselves, but we do have a central core banking services group that will build or partner with us to help build any API that is going to be enterprise-wide. Plus, we have some applications who have gone ahead and built their own APIs into Ignite just for their small use case.
Okay. Another question from the chat here. What is a ballpark estimated maximum throughput that you've personally seen in production operation?
In production, it's a good question. We're still working through a lot of load testing with this to see how far we could actually push this, and we actually haven't broke anything yet, which is good. We could handle quite a few. We have probably a couple million, 3 million update operations a day that we'll put into Ignite caches through those polling services, and probably the same for the read operations.
Excellent, good. Okay. Another question. What applications do you have using the platform? And do you have any interesting use cases?
Yeah, definitely. We have right now a couple very interesting use cases going on right now. We have a group building a IVR system that's going to leverage the customer information that we're now storing at Ignite to build a automated voice service for calling into the bank that will be able to identify people via name and phone number and direct them to the appropriate groups and stuff like that within the bank. And then we also have real-time fraud monitoring, leveraging the Ignite platform, and then we'll soon be the backbone of the web banking application.
Excellent. And then finally, and I think this is the last question, how do you handle redundancy on a single machine?
Sure. So on ZOS, we have them separated into logical partitions. And on our machine right now, we have currently a single logical partition that we are going to be running 2 Ignite nodes on that will be backups of one another, that if any particular JVM fails, the other one can handle the throughput. And then eventually we're going to have a second logical partition on that same machine. So redundancy at the LPAR level, and then hopefully eventually there is going to be a active-active situation with 2 separate ZOS machines running. We also have a machine located in Delaware and one in Buffalo that are identical copies of each other. So if the physical machine itself goes down, all that data has already been replicated and will be stood up immediately at the remote site.
Great. Okay. Well, Tim, we've come to the end. Thank you so much. Thank you for your video, your talk, and thanks for the Q&A.